In this presentation, I would like to introduce the topic lasers, which is a part of engineering physics, which is to be dealt at 1/4 BE first semester level. The contents of the presentation are a brief about the M waves, various light sources, the phenomena of coherence, and the transitions like absorption and stimulated emissions. Then we'll see the requirements for population inversion like pumping process. Later we look at the components of a typical laser system, and as an example we will look at the working of a ruby laser. You are aware that electromagnetic radiation, popularly known as EM radiation, is produced when a charge is oscillating. An electromagnetic radiation consists of an electric field E and a magnetic field B, which are perpendicular to each other and also perpendicular to the direction of propagation. Like any other light, laser light is also an electromagnetic radiation. Now we look at the various light sources. You might have seen a light source which emits various colors, and you observe that when a white light passes through a prism, it splits into 7 colors. So a source of light which gives out spectral lines or group of wavelengths are called as composite light sources or simply white light sources. But in many practical applications we require monochromatic sources. Sodium vapor lamp, even though it consists of two lines D1 and D2, it looks on average yellow with a wavelength of 5893 Armstrong units. But lasers, on the other hand, they are purely monochromatic and they show high spectral impurity. This property makes lasers an advantage in various applications. Look at the acronym laser. Laser means light amplification by stimulated emission of radiation. Hence, laser is a light radiation which is produced by the process called stimulated emission, in which amplification of light takes place. Hence, laser is a light source or a device that generates light of coherent nature by the process called stimulated emission. Look at the history of lasers. Way back in 1917, Einstein predicted that it is possible to produce a coherent beam under certain circumstances. When a photon is illuminated on the material in turn generates a photon of having exactly the same energy, that is frequency, phase, polarization, and direction of propagation or directionality. Now look at these figures. In the first figure, there is no phase relation between the lights emitted by the source. Each wave is coming out at its own phase, and thereby they are propagating in such a way that not to maintain a constant phase difference. But in the later case, all the waves are maintaining a constant phase difference. In the first case, where the waves are not maintaining the same phase relation, the source is called incoherent source of light. But when two sources emit light waves that have same frequency and also have definite phase relation, maybe zero or maybe any constant difference of phase, are called coherent sources. The sunlight consists of large number of wavelengths. and they don't maintain the phase relation. Hence, it is an incoherent source. In case of LED also, the light waves are not in phase, therefore they are incoherent. In case of laser, if you look at the bottommost figure, all the waves are starting at the same point, or they are differed by some distance, but as they are propagating, they are maintaining the same phase relation. Such sources are called coherent sources, and the phenomena of maintaining a definite phase relation is called coherence. The mechanisms that are involved in absorption and emission of light are three categories. One is absorption, this is also called as induced absorption. The other and the second one is spontaneous emission, which results in incoherent beam of light. And the third one, predicted by Einstein, produces coherent beam of light called stimulated emission. Now look at one by one. We will now define what is an induced absorption. Consider an atomic or a molecular system on which a light of energy h mu, which is equal to the difference between the two energy states E1 and E2, nominated as ground state and excited state. If this energy is absorbed by the system moves from ground state to excited state. And such a transition from lower energy state to higher energy state with the help of absorbing the external energy from an external source is called induced absorption. According to Einstein, the rate of induced absorption, that is dN1 by dt, is directly proportional to the energy density of the incident radiation, that is energy per unit volume, and it is also directly proportional to the number of atoms present in the ground state N1. Here B12 is called Einstein coefficient of induced absorption. Now look at the next process, the spontaneous emission. The name itself is telling spontaneous. That means we are not giving any external energy or excitation for the atomic system to take a downward transition. That means suppose that the system is already in excited state and the lifetime of the state is 10 to the power 7 minus 7 seconds. So after the lapse of this lifetime, the atoms which are there in the excited state E2 by themselves spontaneously fall down to the ground state, giving out a radiation equal to h mu, which is in turn equal to the difference between the two energy states. That means atom is initially in excited state and it is losing one photon or giving out one photon as a radiation and coming to ground state. Such a emission in which the transition is from upper level to lower level is called spontaneous emission. As we are not supplying any external excitation, according to Einstein, the rate of transition from higher level to lower level, that is dN2 by dt, is proportional only to the number of particles at the excited level. Here A21 is called Einstein coefficient of spontaneous emission. Now we'll see the third one, that is stimulated emission proposed by Einstein. Suppose the system is already in excited state, but that state is different compared to previous discussed spontaneous emission of excited level. There the excited level has a lifetime of 10 to the power minus 7 seconds. Here the excited state is having a lifetime more, which is typically 10 to the power minus 3 seconds. So this energy state which has longer lifetime or long-lived state is called as metastable state. So metastable state have longer lifetime. So if the atoms are living long time, we have sufficient time to shine the system by a external energy or photon energy whose frequency is exactly equal to difference between the two levels. If a photon is supplied, then this photon, while moving in the atomic system, supposes that there are atoms which can also give out the same type of photon if they are bring to ground state from the metastable state. That means there is a sort of resonance phenomena involved in this process. Therefore, a excited one will now give out the light rays which are coherent in nature. That is, if one atom undergoes spontaneous emission and gives out a photon h mu, and this photon, while moving in the atomic system, initiate another atom to release one more photon. Thereby we have two photons of same frequency and same phase. Thereby there is a coherence. In this case of stimulated emission, the rate of stimulated emission is directly proportional to the incident radiation and also directly proportional to the number of atoms in the excited state. But how do you get this state? That means to get a stimulated emission, we should have more number of atoms in the excited state than the lower energy level. So the mechanism which we use to lift the atoms from the ground state to the excited state is called pumping. The phenomena of having more number of atoms in the excited state than the ground state is called population inversion. We know that in general, under normal conditions, there are more number of atoms at the ground level or low energy levels. If I invert the population, that means if you achieve more number of atoms in the higher energy level than the lower energy level, we have a situation called population inversion. So a population inversion is the condition where you have more number of atoms in the excited state than the lower energy level. So to achieve population inversion, we use pumping mechanisms. This pumping can be done by using optical means, electric discharge, forward biasing, or by chemical means. Now let's see what is population inversion, how it is achieved. Suppose say I have given an energy h mu dash. This energy takes the electrons to excited state E3, but E3 is short-lived. Therefore atoms, while coming down, find an intermediate state whose lifetime is more, which is called metastable state. Therefore atoms quickly undergo a downward transition and comes to metastable state where they stay more time. Now out of this, atoms in the excited state, so at least one of them will undergo spontaneous emission and gives out a single photon, and this photon is having a frequency equal to the difference of energies between the two levels E1 and E2. And this photon, when making to and fro motion in the medium, makes another atom to take a downward transition, and there is an occurs between the first photon and the atoms, and at resonance energy transfer is more and all the atoms undergo transition and produces waves of same frequency and same phase. Thereby, the output is a coherent beam. Such a coherent beam is called laser. To get laser light or lasing action, we require certain points. So these are called components of laser. A laser system consists of the following components. To excite atoms, we want a material or a substance that can provide atoms, molecules, or ions. The substance that provides these atoms, molecules is called active medium. In the active medium, you may have a host material and an active center. Active center really participates in lasing action. Now, to get laser action, we should have more number of atoms in the upper level than the lower level. This is called population inversion. Population inversion is now achieved by pumping mechanism. So, by pumping atoms from lower level to higher level, we achieve population inversion. And by spontaneous emission, we'll get a matching photon, and this matching photon undergoes resonance with the atoms in higher energy state, and there will be a subsequent emission of light. And this whole system, which makes the photons to make to and fro motion, is called resonating cavity. As the lasers are producing light, they may get heated sometime. So therefore, some laser systems require cooling arrangements. Now, types of lasers. The lasers are divided based on the active medium, the state of the active medium, the number of energy levels involved, and the output given by them. So if the active medium is solid, then it is called solid state laser. If it is a semiconductor, it is called semiconductor laser. If the active medium is a gas, it is called gaseous laser. If it is a liquid, it is called liquid laser or dye laser. If 3 levels are involved, or 4 levels are involved, or multi-levels are involved in lasing action, then we call them as 3-level, 4-level, and multi-level laser systems. Some lasers gives the output continuously, some lasers produce output in pulsed manner, discrete manner. So those lasers are pulsed lasers, and which are giving continuous output, they are called continuous wave CW lasers. Let us look at ruby laser. Now we have seen that the active medium is the first component of a laser system, and ruby rod is the active medium. Ruby rod is a combination of Al2O3 and a small percent of chromium oxide. Here Al2O3 is the host and chromium is the active center. And population initiation is achieved by pumping with the help of a xenon flash white light, but in the white light we use 550 nanometers spectral line. And the ruby rod, two ends are polished in such a way that one end is 100% polished, the other end is 99% polished. These two polished ends of the ruby rod acts as a resonating cavity. Suppose that we have population inversion and photons are generated and by spontaneous emission. So if one photon is coming down, it initiates another atom to release one more photon. Now 2 photons will move in the ruby rod and they get reflected at the ends. While going, they initiate 2 more atoms to release 2 more photons. Therefore, we have 4 photons. These 4 photons in their motion or journey excite 4 more atoms. This is a cumulative process, and you have many number of photons released in this one. Once the intensity of laser light increases to certain level, it will come out from the less polished end, as shown in the figure. And this is the energy level diagram of a ruby laser in which 3 levels are involved. And we have helium neon laser. Now these are the components of helium neon laser. and we also have seen a cooling system, and the laser output comes from 99% polished mirror. And the semiconductor laser also have these components similar to what we have discussed for ruby laser and helium neon laser. Then it is, thank you very much.